Good day. In this lesson, we will learn how to draw ray diagrams for converging lenses. But before we proceed, there are a few things that we need to note. First, all real rays of light are drawn as solid lines with arrows indicating their direction. All virtual rays and images are drawn as broken lines. We draw rays from the tip of an object at a point off the axis so that we can find the size or magnification of the image and which way it is. The image is described by answering the following questions. Number 1, is it real or virtual? How do we determine if it's real or virtual? Well, if the light rays actually meet up with each other, then it is a real image. If the light rays move away from each other, then it is a virtual image. All right. In other words, if the light rays do not actually meet up with each other, they diverge, in other words, that's a virtual image. Is it inverted in any way? When you look through a lens, you can see an image that is upright or upside down, aka inverted. So when you draw a ray diagram, if your image is pointing in the same way as your object, we say it is upright. If your image is pointing in the opposite direction, then we say it is inverted. How does its size compare with the object? Is it diminished, meaning smaller? Is it the same size? Or is it magnified, meaning bigger? You have to state which out of those three is the case. And where is the image? Meaning, is it on opposite sides of the lens compared to the object? Or is it on the same side of the lens as compared to the object? It's sort of like a four-way test. It's not Rotary's four-way test, but it's a lens's four-way test. Also, it is often helpful to mark on the axis the positions 2f on both sides, which are twice the focal length from the lens, because this is the object distance at which the object and image have the same size. So when it comes to converging lenses, we can draw 3 rays. This first ray is parallel to the principal axis. Any ray that is parallel to the principal axis will refract in such a way that it goes through the principal focus. In other words, all rays that come in parallel to the converging lens go then through capital F on the opposite side. The second ray we can draw is basically the reverse of this. If we first draw the ray coming through F on the same side of the lens as the object, when it reaches the lens, then it refracts in such a way that it now travels parallel to the principal axis. And finally, the easiest ray to draw, the ray that goes through the optical center. Why is this the easiest ray to draw? Because remember that we learned in our last lesson, the optical center has a special property. It is the only point in a lens where a ray that passes through it is undeviated, meaning, in other words, it continues in a straight line. That's why I say this is the easiest ray to draw. It just goes straight through in one straight line. You don't have to worry about it going this way and then that way. Just draw a straight line through the optical center L. Some other things to note when drawing a scale drawing. The lens is represented by a line at right angles to its axis. So when we draw a scale drawing, we don't have to draw these two curved sides. Okay? We just draw a line straight up. In other words, all we need to draw is an x-axis and a y-axis. The scale chosen for the distances from the lens do not need to be the same as that chosen for the object and image heights. In other words, your x-axis scale and your y-axis scale do not have to be the same. But both scales should be given on the diagram. Use a scale which is simple to use, but which makes the diagram fill most of the graph paper. So a scale which is not simple to use is one that involves 3, such as 1 to 3 or 2 to 3 or 3 to 5, anything like that is not a good scale to use for any scale drawing or graph that you use, right? Because you will be estimating where to draw and what values you will actually read from your graph. So let's look at an example now. An object 6 centimeters high is placed 20 centimeters from a converging lens of focal length 8 centimeters. Find by scale drawing the nature of the image. So here we have our x-axis and our y-axis. This is the optical center L. Our horizontal scale on the x-axis is 1 square represents 2 centimeters. The vertical square is 1 square represents 1 centimeter. So here I have capital F at 4 little squares away from L. Since it is a focal length of 8 centimeters, then 8 divided by 2 gives me 4 because the scale here is 1 to 2. So 8 divided by 2 gives me 4. So that's 1, 2, 3, 4. And then another 1, 2, 3, 4, I place 2F. As I said, it is customary to place F and 2F on both sides of the diagram. Next, I draw my rays. So the first ray I draw from my tip top of the object goes parallel to the principal axis, and when it reaches the lens, in other words, when it reaches the vertical axis, it then refracts to go down through point F. And I keep on drawing that and I extend it. I extend it as far as I can on my graph paper for the first ray because I do not know how far I will need to extend it. The second ray I draw to go through F on the same side of the lens as the object. And then when it reaches the lens, in other words, the vertical axis, then I draw it to go parallel to the principal axis. And right here where these two rays meet, that is where your image is located. You, for accuracy, if you wish, can also draw your third ray, which is the easiest ray to draw, which goes right through the optical center. And if you do your work accurately and draw that third ray, it should also meet up at that one same point. If you draw all three rays and they do not meet up at the same point but make a little triangle, then you are not as accurate as you could have been in lining up your ruler with your points and so on and so forth. So whenever we do a scale drawing diagram, we should answer our 4 questions. The first one, is it real or virtual? Well, here I see that these two light rays actually meet up at this point, so that means it is a real image. Is it inverted in any way? Well, when I look at my object here, my object is pointing upwards. My image is pointing downwards. Since they are pointing in opposite directions, then that means it is inverted, an inverted image. Is it bigger, the same size, or smaller, magnified, the same size, or diminished? How do I know? Well, when I look at my object here, 1, 2, 3, 4, 5, 6 centimeters is its height, as stated in the problem. But the image, 1, 2, 3, 4. 4 is less than 6, therefore it is diminished. And then, finally, I should know where it is. Is it on the same side of the lens as the object or on the opposite side of the lens as the object? So here I see it is obviously on the opposite side of the lens of the object, and in particular it is 1, 2, 3, 4, 5, 6, 6.7 squares away on the other side, and using my scale, 6.7 times 2 gives me 13.4 centimeters. So the image distance is 13.4 centimeters. I have that my image distance is 13.4 centimeters and my object distance is 20 centimeters. Using those, I can calculate the magnification. I could also calculate the magnification by using the image height and the object height. Since the image height is exactly 4 and the object height is exactly 6, then V over U, 4 over 6, gives me 2/3, or as a decimal, 0.67 to 2 decimal places.